Okay, so let's try to start on time. Thank you very much for coming. I think we have ahead of us a very, very interesting, slightly unusual and quite long afternoon of science. So I hope it will be worth your while to stay with us until the end. I will tell you a bit more about the details of the program as we go on. In the meantime, let me introduce Ignacio Pagona-Barraga. For those of you who do not know him, he is the director here at CECAM, and he will get the proceedings started. Yeah. Thank you.
Okay, thank you very much for coming, and thank you. Welcome to this new initiative that we have decided to put together with MARVEL here at campus. This series of classics in molecular and materials modeling. Actually, this has come out because we, CECAM, are celebrating our 50 years as an organization this year. CECAM has been a pioneer in identifying how to promote scientific collaboration in the area of computational modeling right from the very beginning by bringing together the experts from all around the world, and at that time it was in Saclay, benefiting from supercomputing facilities. That's not a need anymore nowadays, but CECAM has promoted or has been thriving and leading the community over all these decades. And when, because of these 50 years, we were thinking what CECAM has accomplished, how we are leading, how we can better lead the community, we have realized that one of the outcomes that sometimes is not so appreciated is the fact that by bringing people together, CECAM has become a natural place for the development of algorithms and new computational models. And that's really very much to the core of CECAM, that has put the effort in the scientific endeavor of having new algorithms that allow us to exploit computer machines to do science with them. So because of that, then we have tried to look into this opportunity to look back into these methods or into these algorithms that have become, with time, looking now with this perspective of 50 years, milestones in the development of the field. And we have approached the creators, the people who really did it, and with the idea to invite them here in EPFL to provide a special type of event where we combine a set of lectures where you can listen and learn from the inventors of the algorithms, how they did it and what is behind, and also, because they were since the beginning, how this has evolved and why these algorithms have become so central, and we nowadays can identify them as milestones. And beyond that, because they are here, I think it's also good to have the opportunity to talk with them and to know about the background and the stories that lie behind this idea, which is something you cannot get easily by reading the papers or by following the published material or chapters in books, because these are really now things that you find in textbooks. So I think that the combination of two will give us a broader perspective of what these algorithms have brought, how they have allowed us to move forward, and also for you to have the possibility to know better what's behind and interact with that. So in this series, for the first one, we have selected these algorithms on molecular dynamics for constraints, for holonomic constraints. And actually, this is the first paper that was published in 1977, numerical integration of the Cartesian equations of motions of a system with constraints, molecular dynamics of N alkanes. And that was done by Jean-Paul Ryckaert, Giovanni Ciccotti, and Herman Berendsen. And we have here with us today Jean-Paul Ryckaert and Giovanni Ciccotti, who will tell us they were really the driving force in this first work that has continued and has expanded, and we will hear how that happened. Actually, I think this is a good example for probably, especially for younger scientists. I mean, we have all this pressure to publish in these fancy journals, And you can see this was published in Journal of Computational Physics. This is not a fancy journal. I don't think it was a fancy journal at that time. I was not there, but they will tell us. But this is a paper that stands by its own and tells you that if you have an idea, it's recognized. You can see that it had received, well, depending where you look at, Web of Science, Google Scholar, but above 12,000 citations and 15,000 if you will look into Google Scholar, which I think it's a clear measure of the impact that this work has had. And again, beyond all these quantitative measures, I think that probably a more clear indication of the impact and relevance of the shake algorithm that came out of this work is that you find this algorithm in, I would say, most, if not all, these community packages that probably you have been working with. You can find it in GROMACS or in NAMD and LAMPS, I would say in all the MD codes, but also, not only there, if you look into ab initio codes like CP2K, Quantum Espresso, it is there. Why? Because in the Karp-Marinello molecular dynamics, you need to impose the constraint of the orthogonality of the energy levels, and that is done also with this algorithm. So this is also an example of, obviously, you saw the title of the first paper that was motivated by alkanes. We were here at the story, but I can imagine that at that time they didn't imagine that this algorithm could be useful also for these other completely different areas or algorithms, but they have been used. So probably, I would say most of the people here in the audience will have used one of your algorithm and then shake is in there. So I hope we will benefit from this, the insight and the story of how this started and how this has changed, how we can operate with molecular models and algorithms. And now, to start with the actual event, I'll pass the word to Sarah, who will tell you about how we organize, and we will listen to the lectures of Jean-Paul and Giovanni.
Yes, thank you, Ignacio. Just very, very briefly to give you an idea of what's ahead. We have separated the activities of the afternoon into a first part, which is the technical part, 2 lectures. The first one by Jean-Paul and the second one by Giovanni. The first one really focuses on the mechanics of constrained systems and on the derivation of the shake algorithm, which is how this whole story began in 1976-77. And then Giovanni will instead cover, I would say, more advanced, or if you want, slightly more formal aspects of the theory, which is how do you tackle the statistical mechanics of a system subject to holonomic constraints, and even beyond that, do a system under holonomic constraint sustain a treatment of equilibrium and non-equilibrium statistical mechanics description, which can be formalized with the same level of rigor and usefulness as unconstrained systems. Okay, so these are 2 technical lectures. I have seen the slides. I would say that we are aiming at an upper graduate level of preparation in order to fully enjoy the slides. But both Giovanni and Jean-Paul are talented speakers who will enable us to follow the flow and the logic of the algorithms, even if the equations are substantial, I would say, in these 2 talks. Okay. We have the idea for this part of the lecture is, of course, you're welcome to interrupt and ask questions. I would ask you to limit questions during the lectures to really moments of panic in which you do not understand what an equation is meaning, or some very technical things, so that the answer can be kept short. We have set aside a little bit of time at the end of each lecture to enable you to ask more general questions about the use or the implications of the methods that you will hear about. Okay. This is the original purpose of these short breaks that you can see here after each one of the 2 lectures. They are short, they are about 10 minutes. I think that we are young enough and healthy enough to sustain 2 lectures of this kind, one after the other, but I am famous for being wrong about these sort of things. So what we will do is, after Jean-Paul's lecture, we'll ask you to tell me if we need a little break just to get up and stretch before we dive into the statistical mechanics. Okay? Once the lectures, the formal part of the meeting is over, we're going to move to what Ignacio was describing as an opportunity to go beyond the technical stuff. So also to understand a little bit how something like a method that then has such a big impact comes to life. What were the problems that these people were interested in? What was their way of working? How were things evolved from the 1970s until today in the way we do computational physics, following the thread line of constraints and shape. We have set up 3 chairs. This is to underline the fact that we want this to be very relaxed and informal. I have a few questions to get the game going, but even in that part of the discussion, you are more than welcome to follow your curiosity. We are here to exchange and learn from each other. Now, both Jean-Paul and Giovanni have, of course, had a rather illustrious and full career following the 1977 paper of constraints. They both have done other things in life. But for us today, they are the guys who invented the shape method and the formula of constraints. So I am not going to provide any long or formal introduction about them. And instead, I would like to invite Jean-Paul to come and to get us going with molecular dynamics of constrained systems.
Okay.
Thank you.
Okay, so thank you for giving us the opportunity to go back 45 years back. My friend and colleague Giovanni has worked much more longer on constraints than me. I stopped basically in the end of in the 80s. So for me, giving this lecture is a bit unusual. I was doing this 40 years ago. So sorry for my maybe bad explanation, but please ask questions if there's in the audience. Okay, so indeed, I will mention people, I will mention CECAM, but all this will come back in the last part of the discussion in detail. I will just mention these people when it is relevant to what I'm explaining. So my talk will be divided into some section. After 5 minutes introduction, I will mention the Lagrange equation of the first kind, which are the proper mechanical equation to solve a system of point mass subject to holonomic constraints. And this will be done with the idea, which was my topics in fact, of classical simulation for molecular systems made of atoms being connected by covalent bonds, for example, and so being permanent assemblies in the system, but interacting into a large number of molecules with periodic boundary conditions to solve concretely, to look at condensed phases. So the particles which are in discussion here are atoms, or sometimes united atoms, beads of polymers, monomers, or something like that. Okay, so you can express this equation of motion, but when you come to an ordinary finite difference numerical algorithm to produce time trajectories of this system of many molecule interaction, you face a problem. We will see the nature of this problem, and then the next point is how we solve that problem, and this is the famous shake method or the constraint method. I will then briefly cover some statistical mechanics aspect because we later on we applied this method to different ensembles of statistical mechanics, controlling temperature, controlling pressure, and so on. And then I will, if I have time, mention something which is very relevant to the modeling, not really the way to solve the equation. It's that, in fact, there is a profound distinction between models of systems with holonomic constraints versus systems where there is no holonomic constraint, but a stiff potential with a force constant going to infinity. And finally, I will show that there is discuss some perspective. Okay, I have to get used to this. So for the introduction, this was the time of the 70s, and at that time, the computer had become very powerful, and people could solve statistical mechanics system in terms of microscopic variables. So they could take a large number of molecules interacting via some force field and getting averages, statistical average, and connect with thermodynamics by explicitly following the sampling of the microscopic variable. But 95% of the paper, if not more, were concerned with the two basic models, the hard spheres and the Lennard-Jones, for which the big names are Alder for hard spheres and Anis Rahman, who gave this name to this hole, and Verlet and others. And at that time, in the early 70s, there were a few studies going a bit to more complex molecular systems. And this was a work of Harp and Bruce Byrne on carbon monoxide, or of the French group Barrias and Lévesque on nitrogen. And they were modeling these diatomic molecules, or with an explicit intramolecular potential, like Morse potential, or they were treating them with another constraints as rigid, hot. And then there was, at that time, a lot of activities by Monte Carlo on lattice to study polymers on lattice to test some theoretical developments of polymers on lattice for which the configuration entropy is very important and so on. This was much in the fashion at that time, and it was actually the specialty of the group where I started to do my PhD. So in 1971, the same Anis Rahman, after working a lot on Lennard-Jones system, Argon, he published with Stillinger, who was a specialist in the water potential, the first MD study of liquid water using a rigid body model for water. So they had naturally worked into generalized coordinates, the three center of mass of the molecule, three Euler angle to specify the orientation of the molecule, and they were solving the equation of motion, the Newton's equation of motion for the center of mass, and the Euler angle, the Euler equation of rotation, by specifying a Cartesian reference frame attached to each molecule and following the Euler angle in time with some technical problems that are not interesting to mention here. And so I got from my advisor, as there was another student doing polymers on lattice, he said you should try to do something on polymers in continuous space. And so the idea was to study N-alkanes. N-alkanes are this family of very simple linear molecules of carbon and hydrogen. So simply CH3, CH2, CH2, and so on. It's polymethylene for the polymer version. And in that case, it was essential to deal with molecular dynamics of these molecules which could change conformation to distinguish between soft mode and hard modes, because the soft modes were interesting because that's how the molecule changes conformation, and this was low frequency modes, which were actually classical, while you had a lot of high frequency modes, which ideally should be treated by quantum mechanics, which were giving trouble. We had to constrain them, if you like. So from the start, we used a model which is specified in the next transparency, in which the simplest molecule of the chain was butane. It was the first, if you go to longer and longer chain, it's the first one which has an internal degree of freedom, which is soft mode. And this soft mode is the angle alpha here between the two planes defined by three adjacent points here, 1, 2, 3. These actually are point particle which model CH2 or CH3 groups. They are connected by fixed distance d and fixed bending angle beta, because these were hard degrees of freedom. So the only soft degree is this dihedral angle between the two planes, which is represented here. Now, yeah, maybe it's not exactly this one, because here alpha equal 180 degree was the all trans configurations. That means that when this point is here on the top, in that case, you have the lowest intramolecular energy, and then you had two other minima, so there was an interesting kinetics going on, and there were data about the barrier here from gas phase experiments, and so we developed a potential to represent this barrier, which were a few kT. So by molecular dynamics, there was a hope that we could integrate the equation of motion over a time sufficiently long to get some statistics about the kinetics, intramolecular kinetics. So I will use butane to explain. We did some calculation for longer molecule, but for this presentation, I will stick to butane. And so in that case, you have 3 center of mass degree, 3 angle to specify the orientation, plus 1 internal angle alpha. So you have 7 degrees of freedom, and we have now 5 constraints, because you have, as I said, specified that the length are fixed. So we can list the constraint relationship, which are holonomic, by 3 distance constraints and 2 angular constraints, which are listed here. So the natural way to go to write down the Fortran program was first to get the equation of motion for that object. And I will, in this talk, basically discuss a single butane molecule. I was dealing with a set of butane molecules, but the constraint problem really is, of course, independent for each molecule, so we can concentrate on one molecule. So the potential energy, in this specific case, is just an intramolecular potential. So if you write the Lagrangian of this butane molecule, function of the 7 degrees that I mentioned before, q, and the generalized velocities, time derivative of the coordinates, then you have first to specify how the Cartesian coordinates depend on q. You take the time derivative of that, and then you can apply the connection between the kinetic energy written in Cartesian coordinates, sum over all particles of mass times r dot square, and you get this form for the kinetic energy in terms of the vector of velocities for the generalized coordinates, the transpose vector, and here the metric obtained by the kinetic energy, minus the intramolecular potential, which is expressed in terms of q instead of r. The form of the matrix is given here. It's a sum over all particles of the derivative of Cartesian coordinates with respect to the generalized coordinates. That's very standard. So once you have written this, and for butane, I spend a lot of time to do that, and especially to apply then the standard equation of motion, dLc over dq dot, time derivative minus dLc over dqk equals 0. For the 7 constraints, you get finally in generalized coordinates the equation of motion q dot, q double dot, function of q and q dot. And these are horrible expressions, very long, but it was doable. Then you write the Fortran code and you test it and you find a lot of bugs to solve, and you spend 1 year like that. But finally, the program worked out, and we published a paper in '75 on the butane properties using this approach. Okay, so to solve that, because the velocity, the acceleration depends on the velocity, at that time the Runge-Kutta type of algorithm for the equation of motion was very popular. It has been used by Anis Rahman for water. So we just took the same, and we got reasonably satisfied with this algorithm. I always forget it. I should not go that way.
We are simply very ugly.
Okay.
By the way.
Sorry?
You're very ugly when you pass.
I see. Yeah. This is recorded, so I can't cancel that. Okay. So, good for butane, but now going to alkanes. The project was not butane, it was an alkanes and possibly a long chain. So this approach was completely impossible to follow in a systematic way. So it was better, and frankly, the idea came from my advisor, but it was a quite obvious idea. Let's try to solve the problem in Cartesian coordinates using explicit constraint forces instead of going through all this heavy apparatus of general coordinates. And just at that time, my advisor was invited to a CECAM workshop, and we will discuss this more. But my boss was very busy, so he said, can I send a PhD student who has a problem which fits perfectly the theme of the workshop? The workshop was, how can we do molecular dynamics for long-time events? That was the title. It was organized by Herman Berendsen. So I stop the story here. We go back to the mathematics to go how this can be solved with the Lagrange equation of the first kind instead of second kind, going explicitly with equation of motion. So you formulate the problem fully in Cartesian coordinates. Your Lagrangian is the difference. I realize now that I have this green point. So the kinetic energy minus the potential energy, everything expressed in terms of Cartesian coordinates of all the atoms of all the molecules of your system. And then you have a list of constraints, which are the same for all molecules. This sigma alpha, alpha going from 1 to f. So the standard equation of motion of Lagrange tells you that you have to take this usual combination as for free system, which gives a term mass of the particle times its acceleration, plus dVdr, that's minus the force coming from the potential in the system, both intramolecular and intermolecular, if you include the intermolecular terms, equal minus a sum of all constraints of the constraint force which force the system to remain on the hypersurface which is constrained. So these are forces which are orthogonal to the constraint, so that's d sigma dr, with an amplitude which is a Lagrange multiplier that you can, for the moment, leave like that, because you can then get its expression by imposing that the trajectory produced by this equation remains on the hypersurface, on the constraint hypersurface. And this is, you have to impose that at all time, for all alpha, all constraints, this trajectory should keep all the sigma equal to 0. Okay. Actually, this is not so complicated. What you have to do is simply to take the first time derivative. This, of course, should be 0. So you have a sum over all particles implied by the constraint in question, times the gradient with respect to the same particle coordinate. You take a second time derivative. At that time, you introduce the acceleration, and of course, a product of velocities and a product of gradient here. And then you substitute your equation of motion with the lambda multiplier in the equations, in this equation, sorry, and you get an explicit expression for lambda, as everything is linear. It's very simple to solve. It's a bit ugly, but it's very simple to get. This is the expression of lambda as a function of r and r dot. So you substitute back your Lagrange multiplier in your equation of motion, and you get finally something which looks like this. In terms of the Cartesian coordinates now, the acceleration are a function of the position and the velocities. So this could be the end of the story. You just go to a numerical algorithm and you solve that and you get, in principle, what you want. The problem is that there is a practical problem that you are using a finite error algorithm to solve your equation of motion, and therefore the constraint has no reason to remain perfectly satisfied at longer time if at time 0 you start with initial condition which satisfy the constraint. So this is the sentence which is written here. So if you take initial condition which satisfy for all constraints that sigma is 0, exactly, using then any algorithm to produce a position at time t plus h will give you on sigma an error of the order of the error on the positions. So that's what is written here. And we found that this error that you do at each time step tend to accumulate and to be systematic and make a continuous drifting of the constraints in time. The thing is getting worse because you don't know exactly a priori how many steps you have to do. So to adjust your time step and so on, it's very ugly to have to be in these conditions. So the solution was this shake method. And in order to be explicit, I quickly mention here that we worked with the standard Verlet algorithm at the beginning. Later on, I was very fond of its another version of the Verlet, which is the velocity version. So in the classical Verlet, you propagate the trajectory if the acceleration depends only on the time, on the position and not on the velocities, then it's very simple. You having position time t and at time t minus h, you compute the force at time t, and you plug that in this first line, and you get the position at time t plus h, and this can be iterated as many times as you like. The velocity is computed separately from the position at time t plus h and t minus h divided by 2h to get an estimate of the velocities. In the velocity version, it's more agreeable because the variable that you control are no longer the position at time t and t minus h, but you control the position at time t and the velocity at time t. So you predict using a Taylor expansion truncated after the second order term, the position at time t plus h, and then having this position, you compute the force at the time t plus h, which is here, and you have in memory the force at time t, and so you can combine that to get the velocity at time t plus h. So it's a bit different organization. And so we are with the idea that we would like to use this algorithm to solve the equation of motion, which can be written more formally, but in a way which is appealing for the following part of the talk. We can divide the force into the explicit force arising from the gradient of potential, and G is the constraint force, so it's the sum for that particular atom on all the lambda times the gradient of the constants. Now, so the key point, the key point is explained on this transparency. So let's discuss the standard Verlet. So this is just a repetition of the previous step, except that now R double dot has been changed by F over M plus T over M. In this way, we consider the three first terms, this one plus this one plus this one, as R bar, which means the predicted step by the algorithm in absence of constraint force is the unconstrained step. And this becomes, this becomes now the effect of constraint that you isolate. And instead of replacing this lambda by its expression in terms of R and R dot, you treat this lambda as a parameter that you call gamma, large gamma naught, and you require that the constraints are satisfied no longer by the exact trajectory, by the propagated trajectory. And this is what is written here. Sigma beta, beta is one of the constraints, applied to the prediction based on the unconstrained step plus the constrained force step action should be 0 exactly. And if you do that, you have a set of constraints which needs to be satisfied by your large gamma. These equations are no longer linear, but this can be done by some iteration method. And you can then get the lambda here, put them into the propagated trajectory, and you find an approximate trajectory, but the approximation has not changed. That's a crucial point. The order of the error remains the same, but the trajectory now follows exactly the constraints over the time. And you can then integrate the equation during a long time as you without limit. Now, for the following, let's for the following, just note that if I take one constraint among all of them, it implies, let's call it beta, it involves only a subset of particles, not all particles. For example, in butane, remember, the first constraint was between 1 and 2. Second constraint was between 2 and 3. So if I take the second constraint, it involves 2 and 3. It doesn't involve 1 and 4. So that's why I introduced this notation that this would be Ki beta, means beta refers to which constraint we speak about, and I is the index of atoms which are involved in the constraints. And the whole thing is the absolute index, if you like, would be 2 and 3 for the bond number 2 in butane. So this is the case repeated here. So that's the butane scheme. We look at sorry that this beta has nothing to do with the beta index of the constraint. We look at constraint 2 between 2 and 3, and we impose the constraint. Sorry. We impose the constraint. Oh, I confused this button. Okay, so this is the explicit, not explicit, but half explicit expression for the second constraint between 2 and 3. And you see that it's quadratic, but what I want to insist at this point is that it involves not only the constraint between 2 and 3, but all the constraints which affect 2 or 3, okay? This sum over alpha is over all constraints and will remain in this sum all the terms for which the derivative of sigma alpha respect to R2 or R3 is non-zero. That means that only the constraints attached to 2 and 3, involving 2 and 3, remain in this equation. Nevertheless, it's you have to solve a matrix F by F, the number of constraints, and you have to invert this type of matrix to solve the set of F equation of this type. So one day while we were in CECAM, Giovanni and me, Herman Berendsen, with whom we had talked before, but he came and he was interested in applying this type of techniques to proteins. And for him, solving this equation for protein was too hard. he came with the idea that it would be more easy to solve this equation in another way in which we would treat all constraints in succession. So he came with what we call the shake routine, not to be confused with the shake method. The shake method is the whole method. Shake routine is a special routine where you go over all constraints one by one and you solve the same trick, same equation, but as if this constraint was isolated. So you solve the problem for one constraint. At the end of this step, all the points satisfies exactly that constraint, but you have destroyed all the other constraints. So then you take a next constraint, you do the same, and after going over all constraints, you go back to the first, and going iteratively in this way, you converge to the same solution as a direct Newton-Raphstone method going like that. So that was the idea. So the equations are too complicated to discuss now. You start by putting for the old position the predicted position in absence of constraints. That's the starting point. Then you go over all constraints, and now you have a single term here because you look only at one specific constraint. Over here, one term. So it's very easy to write down the algebra, and you do this for each constraint one after the other, and you go back and until convergence. Okay, you can do something similar for the velocity, but maybe I will just give the idea that you can apply the same trick for the Verlet algorithm, for the velocity version of the Verlet algorithm, except that apparently you have to solve the constraint problem twice. You have once to impose the position satisfy exactly the constraint at time t plus h. And for the second step, you have to impose that the velocities at time t plus h are exactly orthogonal to the constraint surface at time t plus h. But in fact, this is only an apparent observation. If you look, you have to solve this gt plus h before this gt. So you have in memory the lambda at time t plus h. You can then use as a very good starting point to compute g of t at the next step. So this is called RATO, and I will not. It was done by Christian Andersen, I think, first time. I cannot memorize the. Okay, so a few aspects of statistical mechanics. What I've discussed so far is, okay, we take a molecular model with constraints, and I have shown you that in principle we could use Girard's coordinates, but in practice, I've explained you how we can solve the same problem to generate the trajectory using Cartesian coordinates. Now, in order to test your results and conform them to ideal gas results and so on, to look at the free energy of the solvation, whatever you want. When you want to make contact with theory, you need some framework of statistical mechanics. And so you go to the Hamiltonian. So going to the Hamiltonian is standard. You start from the same expression that we have discussed earlier. You look at the conjugate momentum by taking the partial derivative of the Lagrangian with respect to q dot. You get PQ, and you re-express the kinetic energy in terms of the P's instead of the Q dot, and you get just the inverse of the matrix here, plus the intramolecular potential if it's only that term which is in the problem, or the intermolecular potential, of course, added. So that's your Hamiltonian. Once you have your Hamiltonian in terms of the conjugated variable Q and PQ, you have then a macroscopic phase space on which you can compute, well, you can write formally the average for different ensemble. The microcanonical ensemble, EVN, where the total energy, the volume, and the number of molecules is fixed. The canonical ensemble, if the you look at the canonical ensemble to a property which depends only on Q's and not on the P's, on the conjugate momentum, then you can integrate over the P, and what you get by integrating exponential of minus beta, this expression is of course multidimensional Gaussian that you have to integrate. You get this square root of the determinant of the matrix here, function of Q. And you can also imagine another ensemble where you fix the pressure and the enthalpy. Sorry, I'm going too fast. Here, where the enthalpy, the external pressure, and the number of particles are fixed. Okay, so that's the scheme. And Giovanni and I, we worked a lot in the 80s about how to adapt this method of constraints to sample ensemble where temperature or the pressure was fixed. For the microcanonical ensemble, you know the answer because all what I explained was the solution of Lagrange equation of a conserved system. So the energy was conserved, the number of particles and the volume in that sample. So that's standard method. Now, if you go to canonical, there are many ways to couple your system to a thermostat. You can add a random friction, a random force and a friction term to fix the temperature with a Langevin noise, or you can use auxiliary variable like the Nose-Hoover method, or you can also use velocity thermalization. I don't think I have much time to develop in more detail. There are many methods, and we wrote papers on how to adapt this method to the method of constraints. I just give here one example. For the isobaric ensemble, you have to combine your dynamics with volume fluctuations. That was the method of auxiliary variable. So the volume of your system fluctuates, well, according to an equation where you have a mass, the piston times the acceleration term of the volume, equal the imbalance between the pressure you want to impose and the actual internal pressure computed from the virial. And for the constraint, the crucial point was to couple the volume fluctuations to the center of mass and not to the atomic coordinates, because the volume fluctuation could not interfere with the constraints within the molecules. So the equation of motion for the atoms, atom I of molecule K, involves the usual ordinary force and constraint force, plus a coupling term in terms of capital Rk, which is the center of mass of molecule K. In this way, the trajectory that you produce is representative of this isoenthalpic ensemble. You can combine pressure and temperature, which is, if you like. Now, I have 5 minutes? Yeah. Okay. So this will be the last two transparencies. I have explained that for a model with constraints, we could adopt the general coordinates point of view or the atomic Cartesian coordinate point of view. Now I discuss something different. What can we say about constraining a bond? Is that legitimate? There was a big debate in the 70s, and the problem was discussed by many people. And I've shown here two figures coming from paper which have really impressed me at the time. The first is a paper by David Chandler and Bruce Byrne, who were interested in butane just because they were interested in kinetics. Butane is a very simple kinetic model with which you can play. You can couple one butane molecules embedded into different solvent, and you can study the reaction on a very simple case in which the reaction coordinate is obviously this internal angle. And they produce data, and they produce data for butane in water. Maybe I forgot now exactly what was the solvent. And they were alerted by Helfand that they had to take care that in the ideal gas, the butane distribution, the distribution of the ideal angle of butane was not simply exponential of minus beta V, V intra, but that there was a term, not to forget, coming from the integration of a piece, as I've shown you, coming from the metric. And this is actually Chandler and Byrne produced in this paper figure showing the variation of this term as a function of alpha. They call it phi, but that's not a big problem. You see that there are variation of 15–20% over the range of the internal angle. And so they showed here that with or without taking into account this term, they got different results for the free energy observation in their problem. And so that was in 79, and in 84, Van Kampen and Lodder, because this was such a surprise. Actually, Giovanni and me, we were not aware about this problem till 79, I think. Since 79 that we became aware that there was a problem, that the statistical mechanics of constraint system and of equivalent model with stiff bond were not giving the same results. And actually, the most pedagogical explanation came in 84, 5 years later, by a paper by Van Kampen and Lodder, in which they compare the two-dimensional motion. We are in 2 dimensions of a single particle, but obliged to move on an ellipse. So A and B are the length of the ellipse. So the ellipse equation is here. That's the curve K. And so this will be the holonomic constraint on the motion of the particle in 2 dimensions to force the particle to remain on the ellipse. And if you apply standard statistical mechanics in generalized coordinates, the generalized coordinates would be here the angle, for example, the angle where that's enough to locate the particle, you would find a non-uniform distribution. You would find the distribution which is written here. So of course, this distribution becomes Q star is the angle. So if E equal B, if you are back to a circle, of course, this goes to a constant. But if you are on an ellipse, this term is not uniform in Q dot. And so this results is, if you like, dependent of this internal angle variation due to the metric in the butane case, which is much more complicated to solve. Okay, then the origin of this term is simply that the particle tend to be everywhere with the same density per unit length along the trajectory. And this doesn't transfer, of course, in a uniformity of the angle. Now, if you instead consider infinitely stiff potential, so epsilon is something which goes to 0, and epsilon -1 goes to infinity here, times the constraint on constraint to the square, you get a potential field which constrains your particle in 2 dimensions to always lie close to the ellipse, but in a way which is given mathematically in this way. So if you then solve the problem in statistical mechanics and let epsilon go to 0, then you find that in fact the distribution of angle becomes uniform. Just by cancellation, this term is exactly cancelled by 1 over that term, which comes from the fact that the width of the gap here between 2 curves of the same energy. If you like, this ellipse is in the middle. What is drawn here are constant energy lines. So you have one in this way and one in that way. And the width here is larger here and smaller here. And this effect just cancels exactly this one, and you get a uniform distribution for the infinitely stiff potential, forcing the particle to remain on the ellipse, using that mathematical constraining potential. If you use another one, you will find another result. That's but tricky. Okay, so we are aware of this, and so I think no one is doing error. Although I'm not sure. I'm not sure that 40 years after everyone. So I wanted to finish with 2 points. One will be discussed later, is that all this research started during the CECAM workshop on molecular dynamics long-time events organized by Hermann Behrens in 1974. This was 6 or 8 weeks, I forgot, of continuous work by different people participating. And then I was offered to stay in CECAM for many months to do research. The argument was being that there was a big computer, and for the kind of simulation of alkanes that I wanted to do, I had to stay in CECAM or I couldn't continue in Brussels. The computer was too small. Actually, Brussels is not far from Paris, so there was no big problem. And of course, the impact of the constraint method is for sure quantitatively in all the packages for modeling large molecules and so on, in order to eliminate a large number of degrees of freedom by constraints. And I want to finish with an example that I found in the literature now by preparing this talk, is that to show that not only the method of constraints remains these days the very useful tool to solve problems, but also the type of modeling that we were doing at that time remains adequate to study some new problems, but using the same modeling. So it remains a problem to understand how the solvent influence the internal motion in proteins. And if you are interested in this type of friction aspects of a part of proteins, you go back to butane, because butane is the simplest case in which you can do a quantitative test of any theoretical approach, for example. And so there was a study which was published 1 year ago on butane in water, in which they simulate one molecule of butane in water, changing continuously the mass of the water, just to change the viscosity of the water. You see that they get results function of viscosity. That's because they change the mass of the water in a way which is related to the viscosity. And they look at the friction in butane by comparing what they call free and constraints. So don't be fooled here by this expression. Free means the butane I've been speaking about until now. That's a molecule which has 3 bond constraints, 2 bending constraints, and 1 internal angle with a potential like I showed you for the dihedral angle. That's what they call the free butane. The constraint butane, this one, is that in the box they fix completely the 3 atoms of butane. They leave only a single atom to move on a cone to follow the 2 types of dynamics. One, when the alpha angle is coupled to the 6 order general coordinates, the center of mass, motion, and the rotation, and one in which they decouple the motion of the internal angle from these 6 order general coordinates. And they compare what is the friction, and they find that friction is totally different. In the case where the constraint case, they get a friction which is linear in viscosity, so that's the picture of the Stokes law and so on, while the situation is much more complex for what they call the free butane. So this was a pleasure to see that this type of modeling is still used today to do other things in addition to the constraint method. And I thank you for your attention. and I'm ready to ask a few questions if needed. Thank you, ma'am.
Thank you, Jean-Paul. So, questions?
Maybe with a comment.
Of course.
Jean-Paul didn't underline that the propagation of the error is dramatic, not because the trajectory is not exact, because it's destroying the model. If I have a model of water, I have three atoms in a triangle, and I don't conserve the constraint in time. After a few steps, I have molecules that are completely different. So I have no more a model of water. I have a mixture of n components. Okay, so the error in this case is not an error on the sampling of the physical model. I am destroying the model that I want to simulate. So it's what computers call fatal error. I cannot go any further. Okay, so that's important to understand, because it's not something that has to do with numerics. It's something to do with the metaphysics of the simulation.
It has to do with numerics because it's an error due to the finite precision, but the consequences are metaphysical.
I mean, the error that we do in the dynamics in Lennard-Jones is tolerable, because if we are staying on a constant energy surface, we are always doing a sampling of the same model. So this error is not something dramatic. The trajectory is completely crazy. If we are trying to go to the moon with this numerical algorithm, we fail completely our objective. Right? But we want to do only statistical mechanics. So to go around on the phase space with an error is done. But if we win the model, we are winning.
May I excuse myself that I wanted to, that was my real last transparency, I mean, of the seminar, but I had to show maybe the two next. One is to thank Giovanni Ciccotti, not for his question, but for the collaboration. André Belmans was my thesis advisor, who left me alone in CECAM. Herman Berensen, with whom I've been working, actually I did a postdoc there with him. Carl Moser, who died a few years ago, who was the founder of CECAM and who invited me to stay at CECAM. John Orban, a colleague of Brussels, with whom I spent the first workshop. And Mauro Ferrario, with whom we did, Giovanni and me, a lot of developments that were quickly mentioned during this talk, and who actually helped me, and especially Giovanni, to prepare the slides. So
You want to start?
yeah, and I wanted to mention that problem of old people is that they don't remember anything but short time. So I cannot remember what are these three buttons doing. I have always to recheck where I am. So what's that? Let's read this one. Yes, I have put a list of references which have been inspiring me for preparing the talk. And as I said, the paper of Anis Rahman and the different CECAM reports and all these things and the papers that I've mentioned in my talk are there. And I think that this will be made available to those who are interested.
So yes, just following up on that, not only we are recording this lecture that will be uploaded both on CECAM and MARVEL resources, but if you're interested, the slides will also be available for sure on the CECAM website. I assume also material slides. It's going to happen. Also, you can always get in touch with any of us to get more information and more material. Is there a question? Yes.
Maybe I misunderstood after the CECAM routine, you apply all the constraints, right? And the order in which you apply the constraint has no influence whatsoever on the dynamic.
No, the order is arbitrary. What is important is to go over all constraints at each superstep, at each large iteration step. But the order, I've never heard about an impact.
No, even the method is good. And then is the solution of the reach. Of the method is wrong, and then throw to the basket. Okay? And the method is big. So it's not dependent on
The huge advantage of that method is that you have to program 3 lines of Fortran for each type of constraints. You can use the same 3 lines of code, just changing the atoms implied by that type of constraint. I didn't mention also that I've shown you 2 types of constraints, but there are an infinite number. You can invent any one you like. For example, later on, I've done alkanes with explicit hydrogens without introducing the vibration implying hydrogen. So I was constraining them in a special way to avoid this high frequency, but they were there as center of force, as mass point, if you like. This is another topic that I don't know if we, you can, the variety of constraint is infinite, just an imagination. But once you have written down the expression, you just need the gradient respect, the derivative respect to each constraint, and that's all you need to program when this constraint is in your model.
Yes.
So, does the application of the shape algorithm change the error rate of the integration?
Does the use of the shake algorithm change the error in the integration speed?
No. The answer is no. The order is unchanged, but of course the errors are different. But the order wagon is not modified by the type of iteration of shape.
It also doesn't change the property. If the algorithm is inflected, then it stays inflected. Something that I personally quite passionate about.
the order of the algorithm is the same of the order of the difference induced by this kind of procedure. So you are not changing the error, you are just optimizing the prediction. That's very good.
Do we have any more questions? Okay, so now this is like the most delicate moment of this whole afternoon, because I am going to ask you if you think that we should take a short break or just move straight on into the next lecture. Honesty is key, otherwise you're not going anywhere. Okay, this is exactly what happened in class. Beautiful. Shall I just decide, or shall we let? Because if I decide, you know what I'm going to decide, right? So we just move on.
Break.
Huh?
I heard somebody maybe say that.
Sorry?
Should we have a break?
Ah. So let's have a 10 minutes break. So I think the less than 10 minutes doesn't make any sense, okay? Sure. Okay, I think we should restart the second part of the lecture. Giovanni, the stage is yours.
Thank you very much. It's a pleasure. It's a pleasure to be here in an event. You must know a small difference. Jean-Paul is a chemist. I am a physicist. So Jean-Paul detests whatever high mathematics is evoked to solve a problem. I am only pleased when I see the mathematics that is to solve a problem. So our language will be a bit different, but finally we collaborate very well. And normally Jean-Paul points me out that I don't understand good mathematics, and I point out to Jean-Paul that he is right, but that still the high mathematics is good, so it's perfect. Okay? So let me go on and say you what I want to say. I want to use just two slides to recapitulate what we have learned so far, so that I can point out the conceptual point of them. And then I will go on, start trying to reconstruct for you the exact statistical mechanics when I cannot use, because I have generalized coordinates. This permits me to see what is the real difference in between a model in which there are constraints or there are no constraints. And in particular, Jean-Paul missed the opportunity to tell you that to demonstrate that the dynamics he has shown for the isobaric was indeed an isobaric ensemble, was indeed a good simulation, we needed to have the proper formulation of the statistical mechanics in Cartesian coordinates. Okay? But since you consider this digression of the mind, he didn't point out that. Very good. So now, what we have seen until now is essentially that if we want to impose constraint on a system, we have to add to the standard dynamics of the system the constraint. We add this shape for the following very important reason. The reason is the following. When we doing that very well, this you see this form. This is not arbitrary. If there is a constraint, also the time derivative is zero. So the time derivative means sigma dot d over dr of sigma. And d over dr of sigma, the gradient of sigma, is just the vector normal to hypersurface sigma equal to zero. Now, and this tells you that the velocity is always orthogonal to the surface of constraint, which is normal because I want the velocity to stay there. At the same time, the power used, the force that I want to use to keep the velocity tangent to the hypersurface is exactly orthogonal to this hypersurface, which is the force that is needed to bring the system back. And so it has to be proportional to the sigma over dr. And now lambda is just a free parameter, is the Lagrange point of view, which is in principle not determined, if not by the condition that this is what should result, that I have to fix satisfying the constraint. And I am adding a certain number, f number of lambdas, on an f number of surface. So I am overall in this problem exactly n plus f degrees of freedom and n plus f conditions. A differential equation is a condition, and the sigma is a condition, algebraic, but is a condition. So I have the same number of unknown and of the condition, so I can solve the problem. Okay. Oh, now, as Jean-Paul has pointed out, I can solve analytically this constraint, and the solution is even very, very nice in principle because it's a linear problem. You see, the lambdas are given. You see immediately that the lambdas are given as a function, explicit function multiplied by the inverse of a matrix. So it's just a linear equation. So it's simple, although the dimensionality can be a problem. Okay. Now I want to stress once and for all that although many, many people in the world consider shake the subroutine shape, so that there is a large number of stupid people that to get some reputation baptize with different names the algorithm to solve the shake equation. There is only one shake, that is this equation to be solved, which tells you predict the position of the system at time t plus h, but you don't know exactly what it will be because you don't know the constraint forces. And now you block and you determine the constraint forces by fixing a lambda such that the constraint is satisfied. So you have just to solve this equation, which is the equation of constraint. If you solve this by Newton procedure, by Berenson procedure, by my Nice procedure, that's totally irrelevant. That it can be very important for the efficiency of the code. Okay, so it's not something that will change the nature of the problem. And in a sense, the discovery that gave us this possibility is that in this way, I am sure that I am not destroying my model. And this is the last point that emerged in the discussion. If I do in this way, and I don't use the approximate form using the force of constraint with lambda explicit, but I use my force, I have a difference in the satisfaction of the constraint, which is the difference between the analytical value of the lambdas and the lambda I found by shake. And you can demonstrate immediately, this is a trivial development, that this difference is of the order of the algorithm. So you are not violating the precision of your algorithm, you are only optimizing the point in which you will end up at time t+h. Okay? So this is why this is an exact algorithm, and this is why essentially there is no possible alternative. Okay? And it's been very nice because applied mathematician went very excited by that, and they've demonstrated that this is symplectic, it conserves the time reversible invariance of the system, etc., etc. So, in a sense, is the only way in which the argument can be taken. Now, by analytical mechanics, in general, and this is already, you have already seen that, if I introduce the Q's variable means a number of variables that is the difference between the degrees of freedom and the constraint. I have a relation which is not invertible, and that's the point. I'm not representing the same motion on the same space. I have a system of n degrees of freedom, or 3n if you prefer, okay? And since I have constraint, I have only a more limited number of degrees of freedom. So the meaning of the standard analytical mechanics is very different in the two universes. In a universe, I am reducing the freedom of my motion. In the other, I have free moving, but in a manifold that is differential geometry, etc., that is much more complex. Is the manifold, the Riemann manifold of the Q variables. Okay. Now, for that, we want to know something about the statistical mechanics of the system. And as Jean-Paul has said properly, we know that since the system is an Hamiltonian system in generalized coordinates, what's happening here? Why is that?
Double click.
Ah, okay.
Again. Go.
Okay. Now, I know that I have in general, I told before, no, that our trajectory in molecular dynamics, in spite of the name, is not an exact mechanical solution. We are not looking for an exact mechanical solution. We are looking for an exact sampling of the phase space, normally. And we want a limited coherence of the dynamical trajectory for a short time. This is what we care, really. Okay? Now, if we want to consider that we are phasing a sampling, of course, we want to associate to this activity of sampling a theoretical probability. The probability is a conserved quantity because the integral over the random variable of the probability has to be 1. So I have a conservation law, and the conservation law is written in this way. And if the system in generalized coordinate is Hamiltonian, we know that the phase space compressibility is 0. And so we know that the conservation law becomes the Liouville equation of motion, which is, by the way, is the adjoint of the evolution of the variable, but this is irrelevant. And then, in generalized coordinate, theoretically, we have the probabilities for the microcanonical, for the canonical, etc. But this means, especially when I don't know what are the Q variables, and for a polymer, for a protein, I never know what are the variables. No one. There is a book like that that is just written to write generalized coordinates for a protein. And I mean, it's very limited use, and certainly no mechanical. Then, if I want to have a correspondence between my dynamical activity and my statistical mechanics, I have to do something more for that. And now this is not automatic, so we need to do a small tour, and this, we made this with Jean-Paul in 83, 82, 83, essentially. So it took 6 years before we could realize what to do in this case. And this was done in the following way that I like very much. Because take the RP. I told you that the Q are not enough to do an invertible transform. But the sigmas, if the constraints are not too stupid, the sigmas are also possible generalized coordinate. Sigmas are function of R. So if I consider now n degrees of freedom, of which F are the sigmas, no more sigma equals 0. Sigma is function of R. And the other are Q. The set Q and sigma is then giving to me a full set of coordinates, and will be invertible with the R. And then, of course, I can associate, because I have the Lagrangian description, to the Q's, PQs and P sigma. And so I have a total description of my system, the free system, not the constraint system, in this new representation. And this is also what is called, in Hamiltonian dynamics, a canonical representation. The system is invertible. And let me call, because I need to short up all the language, let me call this double set of variable U, PU. Okay? Then, of course, if I have a Lagrangian, I have a Lagrangian in the new variables, which is a function of U and U dots. And if I want, I can also do a Legendre transform and get an Hamiltonian H and H star which is still identical, is the identical motion of the system in the full free space. No one has done nothing. But now, of course, the PU are not simply the mass times the velocity, but there is a metric matrix. And so now the PU are a linear function of the velocity, but much more complex in principle, even more complex. Now, one of the reasons why people, the historical people, have done the description of the mechanics, not only in Lagrangian, but also in Hamiltonian language, and you will admit with me that you do statistical mechanics only in Hamiltonian language, never in Lagrangian language, is because the Lagrangian equation of motion are what is not called a normal system of differential equation, because the highest derivative, the acceleration, is multiplied by a matrix, which is depending on the coordinates. So the system is much more difficult to solve, and moreover, the position and the velocity are not independent variables. By the Legendre transform, I describe the system by the R and the P, and the system of equation is double order, is R dot equal and P dot equal, and R and P are independent variables. And the state of the system is described in a point in this space, and so I can have a statistical description, a full description of this without any problem, because I have a full description. Is in the free space, and this is sampling of that space. So this is why statistical mechanics only do in Hamiltonian language. So now I want to obtain a relation between these more general momenta and these velocities. And if I write this matricial system in block form, you see that I have a relation between the velocity u dot and pu that I can invert, and I have this simple relation. So now I can do a step forward. And since I know that when I move with constraint, I don't conserve only the constraint, but I conserve all the time derivative of it, because this constraint is valid to all times, then I know that sigma dot will be, in general, if I don't impose the constraint, will be this linear combination E, T, and Z are matrices, will be this linear combination of PQ and P sigma. And if I impose sigma equal to 0, and I have sigma dot equal to 0, then I have that the generalized momenta of the variable sigma, they are not 0. A famous analytical mechanician, a French one, I don't remember the name at the moment, was convinced that the generalized momenta had to be 0 in this case, and didn't see that they were not 0. And they are given by this explicit expression as a function of the PQ. I simply solve here. If it is 0, you see that P sigma will be Z minus 1 minus Z minus 1 ET PQ. Okay? So I have that the specific value of the momenta associated to the sigmas is known. And I know that now to say that I am moving along the variety which has sigma equal to 0 and P sigma equal to this value is exactly the equivalent of my dynamics in full space. And now the Hamiltonian H star, which I can derive because I have an inversible relation, can be taken in the limit in which sigma equals 0 and P sigma is equal to P sigma tilde, this combination, and I will find back the Hamiltonian that Jean-Paul likes very much, which is the constraint Hamiltonian. Okay? But now I can profit of this formal evolution to find the probability, and it's trivial. Okay? We know that the probability, and on that Jean-Paul is perfectly right, if I knew the generalized coordinate, would be of this shape, which tells me not much about the real nature of this object, because the Q's normally are not known, but I can rewrite, it's a small trick, I mean, it's a trick that we do in physics many times. I can write this condition by writing the total Hamiltonian of the total motion, and imposing that sigma equals 0 means delta of sigma. And P sigma equal P sigma tilde is this with a delta. And then I get that if I integrate in the U, the PU space, this is my probability measure. Okay? That's all the mind, that's trivial. And now you remember that I also found that this difference, if I like, can be rephrased as Z minus 1 times sigma dot. The relation that I showed before, matricial, you trust me now, you have forgotten, but they are there. Okay, tell me that this difference is also writable in this shape. But now I also know something. I know that du dpu, since the coordinate transformation between dr and du is canonical, the Jacobian is 1. It's a canonical transformation. So to pass from du dpu to dr dpr is just a change of the measure with Jacobian 1. So I can rewrite this expression as h of rmpr, delta of sigma of r, delta of z-1 sigma dot of r dot dr of dpr. Okay, and now I have in my hands the expression in standard coordinate. This is the partition function of the probability, for example, in the canonical ensemble. For the microcanonical would be the same with delta of h minus z instead of e minus beta h, which is the same. And now I have the explicit expression, because now this I can even, for a small dimensional system, I can sample by my hands. I know what it is. Okay, I have it explicitly. And I can do a nice observation, which will be useful in a second. I can take this probability and reason on the fact that this probability can always be written as the probability in dr times the conditional, what is called the marginal probability. I have taken the integration of the dpr, and what remains is this, times the conditional probability of the PR given R. Now they are no more independent because there are the constraints. Normally, many simplifications in statistical mechanics that we do every day comes from the fact that in canonical ensemble, the momenta and the position are independent. But if there are constraints, position and momenta are no more independent. Okay? And so I need to remember that I have to have here the conditional probability given rate. And if I do this integral, of course here I don't derive for you this integral, but it's something that you can understand is not very complex. The kinetic energy for the r coordinates is just Euclidean. But in Chinese coordinate becomes what is called the quadratic form. So it's a Gaussian integral. So all of us, we know how to do Gaussian integral. If we do the Gaussian integral, we can find easily this marginal probability, because this probability is simply the integral of a dpr, Gaussian integral. And if I do it explicitly, I find this result. So now I know in which way the probability of a system in which I have imposed constraint, local, molecular, or arbitrary, is altered with respect to a free motion, is altered by this matrix z minus z to 1/2 is the determinant of the matrix. This is stupid. Okay, and but this is not very useful. I also know the conditional probability, which is the ratio between the two, and I can write it explicitly. This mu is nothing else than the diagonal expression of the real mass. Okay, and so I have the control, and we use this control to demonstrate that this was an isobaric ensemble. It's not important to go in this detail. I know what to do and how to operate. But now I have something more nice. Now I am accustomed to think that normally I want to sample things without constraint. But if I add the constraint for some sordid reason that I will describe to you in a moment, I like to do something a bit cheat in some way. I discovered that the difference is under my control because it's the determinant of the matrix Z. Okay? And so now I have to digress a moment to tell you that immediately we could do something very, very interesting in which molecular constraints have not more any role to play. It's not the molecular constraint of our problem. Our problem is the following. We know that very often we are interested in what is called metastability. Metastability is the case in which the system likes to spend a large part of its life in a region of a space, A, and a lot of time in another region of a space, almost equivalent, different, but very long. And in between, essentially, it never goes. If I want to know the statistical mechanics of this system, I must know the probability all along the situation. So not only in the region of high probability, also in between. For example, in a chemical reaction, to know the rate of passing from one to the other, I need essentially to know how high is the barrier, say the chemist, which means how improbable is to pass. Okay, because if I know the probability to pass, I know the time that typically something will happen in an infinite time. This becomes a fraction of time that is related to the difficulty to pass. Okay? So this is a metastability case. And very often happens, and in chemistry this is an art, that I can find variables that I call psi of R. Variables that are essentially whose values foliate in the sense sigma psi equals something is an upper surface in my phase space, or my configuration space. Okay? So I have a surface, and changing the value, I change the surface, and so I am producing another description of my configuration space by this foliation. It is called. And this is very often called, in improper language, this is called a reaction coordinate. Okay? This function that describes to me how much I am in the probable or improbable region is called the reaction coordinate. Now, this reaction coordinate is just a function of R. So I can say, what happens if maliciously I say to my system, no, you don't go where you want. You go where I want. So now you stay on the psi value, which is the most improbable of your value. Okay? And now you even tell me how unpleased you are to stay there because I know the entity of your constraint force. Okay, so I know how much you want to escape from there. So under, I am knowing something about your free energy. I say under voice because I am not demonstrating. But you understand that I'm telling you really how the system has to work to bring my there. Okay? Oh, and now I say, but psi of R equal psi cross is a constraint. Oh, and now if I put my system in psi dagger without the system wanting to be there, okay, I can have an idea of what is the probability to be there because I know the analytical formula. Okay? And if you have a system that, as is normally said, is not unimodal, but is plurimodal due to the metastability, so the system is with high probability either in A or in B, you know that in this case, the average value has no meaning. If you compute the variance of a system that has two maxima, this variance tells you that the system can be, I mean, there is no meaning. The variance normally tells you how much I am fluctuating around my average value, but here there is no more average value. So whenever I have metastability, I'm not doing all the chemistry that is related to that, but it's very general. What I normally want to measure is not the average, the statistical average, but is the conditional average to a value of the reaction coordinate. So what I want to measure normally is this quantity, which is the average over the conditional probability of R, given that psi R is fixed, and which is mathematically given this way. And now, what is the difference between this average and the average in which I have used the constraint? Well, the only difference is that I have this Z factor that is perturbing my life. And is a theorem, but is a trivial theorem to demonstrate that I can sample and compute numerically this constrained average by taking the standard average over the hypersurface psi equals psi prime if I take those averages multiply by this unbiasing factor. Okay? So, in a sense, I have taken pleasure to constrain the system to tell me what it does not want to tell me normally, because I have constrained it to be where it does not want to be, and I have simply said what I am sampled for you is not good, but I know that it's not good only for this number. So I add this number, I take the average, and you are out. Now, the left-hand side is normally not something that I am able to sample for the value psi dagger. For the value psi1 and psi2, I sample. But for the improbable value, I don't sample. But on the right, I am sampling. And so, and this is just something that I will not write. Of course, I cannot now give you the probability of this improbable because this is an average. But since the derivative of the logarithm of the probability is essentially the free energy, the effective force. By a kind of thermodynamic integration, I get to the probability. And so I can do, and then I can save in the simulation even an order of magnitude, in the sense is irrelevant. I mean, I'm creating what I can call a Maxwell density. Okay? And for my digression to say, constraints are not at all a trick for simulating proteins. They're also a conceptual instrument to produce situations that are meaningful but are not brutally obtainable by simulation.
Can I just make a very short comment?
Yes.
All this is valid because you want to use molecular dynamics to sample.
Yes.
If you were using Monte Carlo, you could stay the way.
I do the same. Is the non-Boltzmannian sampling, essentially, and I can use alternatively depending what is better. Right. Oh, but in molecular dynamics, and when I want also to study dynamical phenomena, I can't brutally use Monte Carlo, but I can use molecular dynamics, and then I'm using in a unified way, essentially. Okay. Well, now this is a change of subject. In the sense, I left you with my derivation of the equilibrium measure in Cartesian coordinates when I have constraint. But if I want to go to study non-equilibrium, you remember that in principle I have an instrument, is the Liouville equation. But now I have no more the Liouville equation. I want to know what is the Liouville equation of a system in constraint. I know in generalized coordinate, but I don't know generalized coordinate. So I have to find something. And so I would be pleased to be able to derive for you also the non-equilibrium statistical properties of the system, in this case in which I have to use constraint, molecular or non-molecular. Okay? And now, for that, we have to wait for the equilibrium ensemble. We waited, how much? 76, 82, 6 years. That came after Tuckerman and Martina were able to demonstrate that if I have a generical non-Hamiltonian system, so a dynamical system, X now is RMP, okay? If I have a dynamical system in which the G is not derived by dH over dV minus dH over dr, so it's not Hamiltonian. If I have a dynamical system, though, of this type, in which normally in time the Jacobian is not conserved, I cannot do trivially statistical mechanics, because statistical mechanics is done normally in the stationary state. In the stationary state, if the measure changes at every time, is not something meaningful. Okay, a system that is evolving is never stationary. And so, in this case, until I have been able to define what I call an invariant measure in time, dxt in an Hamiltonian system is equal to dx0. Until I have found an invariant measure, I cannot do statistical mechanics. Now it happens, and this is just standard elementary analysis, is that the D Jacobian indeed satisfies the differential equation that is easy to derive and tells me that dj over dt, j is the determinant of the Jacobian matrix, is just proportional to j itself by the the function k, which is what is called the phase space compressibility. And then you see that if I integrate this differential equation, I get that j of xt starting from x0 can be always expressed in this form, because this is a definite integral. And in this analytical form, it is simply the difference of these two factors, where w is the indefinite integral of k, of kappa. Okay? So, and w exists surely because this is integrable. This kappa is just a derivative, so that has to exist. So if I do the trivial trick to bring this w there, I have that e minus, not there, sorry, in the differential form here, I have simply that this factor weighting delta xt is equal to the factor at x0 times the x0. So I have no more what is called a Lebesgue measure for my statistical mechanics. I have a new measure that is invariant. So now I can do statistical mechanics, but in this more general space. Okay? And now, if I want, having that, I know, and again, and ridiculously, now I have to use the fact that I know what is the dynamical system in, I know what is the constraint force analytically, is the solution I have given to you, which is a function of x and x dot, of r and r dot, position and velocity. Okay, then I can really derive for you the gamma. Let me show. Now, I have a conservation law, because the conservation law is still there, but now it's no more with P. Is in this new measure, the x gamma times P, and then I have a new Wheel equation, Giovanni's one, which is valid, which is different. As you can see, I've simplified things so that to you this can, if you have followed me, this can seem to you trivial. Indeed, we have to fight enormously on the physical review, because there is a bunch of people that were delighted to have discovered that the standard Wheel equation for a system that is non-Hamiltonian produce monsters, produce collapse of measures, etc., which is normal because the measure is no more invariant. And so they were inventing a fractal structure of the probability density and other monster that really don't exist when to work properly. Was in the family of my, once upon a time, my friend Bill and the company, and they refused the idea that this could be the way to do statistical mechanics. They wanted to do as if the equation was universal. The equation is not universal. It's universal for a Hamiltonian system. Okay, and if it's not a Hamiltonian system, it still can be done for chaotic system, and is of this time. Okay, and now once you have this in principle, and I don't know where I am. In principle, but the chairman will tell me, I can do non-equilibrium. Now, should I do non-equilibrium?
You have 15 minutes.
Then I can do. Okay, at least in part. Okay. Oh, then, conceptually speaking, I've given you the Langevin equation generalized. You do non-equilibrium by I go home. Okay. But if you want to see in which way I can use it and in which way this now getting very simple to do as a simulator, as a molecular dynamics things, you can see that once I know what is non-equilibrium, because I know the generalized Wheel equation for my system, I can do also non-equilibrium average. Now, what is a non-equilibrium average? This is another concept in which you find a lot of strange things in literature. If I follow now Gibbs, I have no more ergodic theorem, I'm out of equilibrium. So the macroscopic properties depend on time. So I cannot say I take the time average and I am done. I can do dynamics, but I cannot simulate. So to explain what is non-equilibrium and non-equilibrium properties time-dependent, I have to take a point of view of Gibbs and say, imagine that I am able to compute the probability density at time t. Then, if I have the probability density, I have all the expected value, the averages of any observable, O is a property of the system, the variable for the pressure, the kinetic energy, whatever you want, the specific heat, etc. But be careful, even with Gibbs, now I have to tell you that this average is not taken over dpdq. It's not taken on the Lebesgue measure. It's taken on this more generalized measure that I have defined before, gamma dx. Okay? So this is what it is now, a non-equilibrium average. And I have to define a way in which I can solve this question, because to solve numerically the Langevin, the generalized Langevin equation is painful. So I have to do something to cope. Okay? And now I want to describe to you at least the first case. The second I will let to your imagination, because it's just working well, has to be demonstrated, but I mean, it's the same thing. Imagine that I want to study a relaxation. So this means that I want to study a problem in equilibrium that is perturbed by a time-independent perturbation and know the response. Instead, I want to imagine that I have at the beginning a system brought out of equilibrium by something, okay, but macroscopically, and then I want to see how it goes back to equilibrium. So I want to study time-dependent averages of this type, and I want to study that in a way that is numerically doable. So I want to study relaxation. Now, look at the very nice formal character of my dynamical system. I told you that when lambda is given in explicit form, the theoretical form that we don't know how to integrate but exists, okay, the Liouvillean, so the operator generating the motion of my system, the Liouvillean of my system is simply writable in this standard way, okay, in which the lambda is explicit, is a function, and if I have an observable O dot is equal this operator applied to O. This you have seen many times in analytical mechanics. An operator, a function on phase space evolves with the Poisson parenthesis, essentially. IL0 is the Poisson parenthesis, nothing. Okay? So you know how it evolves an observable. And now if you look at the Giles-Langevin equation, you discover that d over dt of gamma p is going by minus IL0 plus k. And since I can get rid of this analytical process, but it's simple. This whatever I tell you without doing the calculation is just something that you find in 3 steps. You can get rid in this equation of the gamma, and you discover that dp over dt evolves again with, like was in the standard case, by minus IL0p. And minus IL0p is just telling me that the evolution operator of the probability is the adjoint of the evolution of O. So I'm in something that is standard, appears to be standard statistical mechanics. Then I can go on and try to evaluate numerically, now I'm back a simulator, this average over a time-dependent probability. But since P evolves with the adjoint operator of O, I can take this like a scalar product. This is similar to in quantum mechanics, we call it scalar product in mathematics in general. Okay, and then I can take this operator that operates on P and transfer it on the observable. And I have a to the IL0 TO times P. P is the ensemble I have prepared. P is my initial condition. So I put my system to be in a situation, in a stationary situation it was not. And then simply by computing the observable at time t with my dynamics and averaging over this initial ensemble, which could be an equilibrium, but could also be, if I study relaxation and non-equilibrium situation, I can get this property. And for a molecular dynamicist, this expression is nothing else that my black trajectory in phase space representing the evolution which is sampling my initial probability P of X. This is done by me. For example, I can put my system in between 2 walls with different temperature. So I'm creating a system under thermal gradient. I sample that, and then, for example, I bring my system in such a situation, and I want to see what happens when I turn off this reservoir. So I let the system to thermalize. Okay, and then if I sample initial condition along this fix my mean initial stationary trajectory, and I follow the full non-Hamiltonian dynamics of the system up to time t, is what I call segments, the average, the standard average over this will be a statistical estimate of this non-equilibrium property time dependent. Okay, so I can do in the non-Hamiltonian case exactly what I do in the Hamiltonian case, only my dynamics now is sampling a different Gibbs measure, which is this invariant measure that is there, but it's automatic, it's done by the dynamics. Okay, this is relevant because I promised not to do, and so I can now to the conclusion. And my conclusion is that constraints are a bad beast, but can be domesticated. I like very much the domesticated constraint. They are an horrible object, but we can do whatever we want with them because they can be instrument to define the model, but we can kill the error to propagate the error, and then we can solve a model, a stable model, and solve the dynamics of it, and do the normal statistical mechanics. The statistical mechanics treatment can be done, I mean, requires some algebra, some analysis, but nothing very horrible. The associated equilibrium ensemble can be found and used for much more general theoretical purposes, like the generalized ensemble, the blue moon, etc. And we can carry over completely the program that is came out from Onsager and Kupo, non-equilibrium, time-dependent statistical mechanics, even if the system is constrained. Okay? And of course, I have to thank a lot of people. This is sample of them. I started working with Jean-Paul and Herman. Then this work was done to do the blue moon. Then Tagerman and Martina worked with them to find what was the implication of the non-Hamiltonian dynamics, and so I could derive the other part with them. And I started doing an equilibrium in the Hamiltonian case many years ago with Yakuchi and McDonald in CECAM. So everything was essentially using. Thank you. You wanted me to be fast, but I was fast.
Very faster than I expected, which is wonderful. So, do we have questions? So you press the.
No, please.
So I wanted to ask about this non-Hamiltonian dynamics. How you have the change measure. So, so does it make any? Do you impose any constraint on how the Jacobian evolves, or like for general evolution?
Even in a Hamiltonian system, the system can be not chaotic, and then I see people do statistical mechanics. Assuming that my non-Hamiltonian mechanics is enough chaotic to be able to do statistical mechanics, I can master this behavior by changing the method. That's what the science says. So it can be, and very often it is, that the more general mechanics is not so chaotic. Not good for statistical.
For example, if it's dissipated, right?
For example,
If it's dissipated, then it becomes
exactly, it's surely not the system on which I can do that. I am not speaking of this simple system. I am speaking of a system that has a phase space, the kappa, the phase space compressibility is not zero. Okay. But still there.
The second question.
Okay, so Professor, I wanted to ask why there was this surprise about the generalized linear equation? Because, I mean, to me, as I look at it, it's just a realization of, I call it exotic dynamics, you call it non-Hamiltonian dynamics, but I mean, if you look at a mathematics book like Arnold, it's simply an application of symplectic dynamics, which is not the matrix, the symplectic matrix, not 0, 1, minus 1, 0, is just another one. So I don't understand, and for example, in general relativity, you have always this.
You're pointing your finger on a very interesting point. The point is that Arnold is not readable by chemists.
No, I know, that I understand.
Okay.
But,
And as a result, and even physicists are in trouble, not to say I'm not pretentious. And so many messages don't go through the corporations. So Arnold would laugh at that, would say it's trivial.
no, because I did something similar, of course, after you, before knowing the Martina Tuckerman work. Then I read the Arnold and said, well, it's the same and it's already done.
Imagine normally the writing of Arnold starts, we are speaking of dynamical system. I test system which have a dynamics and a measure. Measure is a mystery normally for physics. Even the free energy is a mystery. Since chemists stay attached to the free energy, and they still didn't realize that the free energy is just on logarithmic scale, the probability. Okay, so I have to reason about a probabilistic system, but it's not the case in their mind. Their mind, they want to the free energy. So a maximum is a minimum, etc. But that's ridiculous and helps a lot in imagining a scheme, a numerical scheme. So this is the reason why I am very pleased that in the last 15 years, a private mathematician got very much interested in simulation. This created a jumping point. So you are pointing out to that the
Yes.
jumping point will require a certain mixing of cultures.
Yes, and let me ask you also this question. I'm interested in constraining time in some sense because your constraints work on coordinates, but constraining time, I guess, can bring a thermostat in life because
No, sir.
yeah, in some sense. So do you think that, so I mean, I read the Tuckman argument about the Nose derivation, their derivation with the Jacobian. And I'm wondering if you can do some constraint dynamics which does not imply
I understand.
does not imply
I understand the question. I don't have the answer, although I'm telling you the steps that I see that tell me that this is surely possible in field theory. Because the only way in which you can imagine such a scheme, and in a relativistic space, in which time is just the default variable and everything is identical, only there you don't have the equation of motion with action at a distance. So the only way in which you can do that is by reformulating the dynamics in field theory. That can be done, but
so you didn't do
I wish you success, but it will require some time.
no, but I mean you did just constraints over the R, you didn't do constraints over time.
I understand the constraint over time. I mean, if I have if I have a dynamical equation which is symmetric in space and time, I can surely define a holonomic constraint in the space-time. Okay? And then I can do only if lost the dynamics of particles. Okay, then it's said, because normally we work on that. And to come back to Tuckman and Martina didn't want to follow your idea. They wanted just to use this non-Hamiltonian dynamics to be able to prove that a stupid dynamics like the Nose one would bring it to the canonical ensemble. And they were successful, but they didn't discuss this aspect. They didn't want to constrain the time. Okay, but it's a nice idea. I mean, only field theory is full of traps, etc. So I mean, it's not my pleasure.
Okay. If we haven't got any more questions, I would just thank again Jean-Paul and Giovanni for these lectures. And then maybe we can move to the let's have a chat part of this evening.
So you have said that we are on the same line.
You sit there, you sit on the center. No, I like you to be in the center, so I can keep you reading. We just need a second to reorganize things around.
This is working right.
Okay.
Yeah, I am in color now.
No, you're fine. Look, we have a fantastic trick. There is a black screen behind you.
Okay.
We have taken care of that. Shall I start, or do you guys have any curiosity about what was going on around Giovanni and Jean-Paul when they first thought about constraints?
I have should I speak?
Yeah.
I have a question about the name. Why is it called shake?
Because you go from a constraint to the next. And
But you say that. Sorry. No, okay.
And then this was a name invented by Berensen, and was invented due to his algorithm, which was the specification of the solution of what now we call the shake equation. But he was calling it shake because what you do, you compute the lambdas by successive readaptation. So you are shaking the system to converge, and you converge only asymptotically.
So it comes from the algorithm.
It's like the shaking of the Martini. Okay.
May I add that
This is the algorithm. And if
the
you
name
solve,
comes from the algorithm, but then
to
and
be
then
honest, if you also use the Newton equation, you have a similar phenomenon. You can go up and down. So, I mean, essentially, you are solving an equation, and very often an equation is an oscillation. I mean, it's a stupid name, but
Jean-Paul wanted to add something.
I want to add something simply that in the original paper of 1977, you get the definition of shake as it was at that time. So the method of constraint, in the title it's written method of constraint or something like that, and how to solve the equation for the lambda, the parameter which would keep shake exactly on the surface with a numerical algorithm, was explained with two alternative methods. One was shake and the other was the matrix method. Okay? So at that time, there is no doubt that shake means only the algorithm, and shake comes from shake, because you shake a few atoms, then you shake another few atoms, and so on, and this converges to the right solution. But then, with time, the name became the whole method.
the name
Now
becomes
there's no more
attached to the
justification.
equation.
no. The people profited of this vagueness for whatever stupid improvement they were doing on the solution of equation to baptize it and claiming to be the author of another shake. And this pissed me off infinitely. So in 97, because this was enough, in 97, I used two typographical characters in a summer school, and they shake is the equation. Okay? Now, whoever solves the equation is solving shake. Oh, and there is a particular procedure that is the first one, which now called in italic shake, which also does the solution of the equation. Okay? Oh, of course, people like Roberto Carr came to me and said, we invented a way to solve our constraint in a way similar to you. And they say you should only go and wash your hands, okay? Because you are stupid, you are using shake, okay? This was my reaction. And we found the peace after.
Does everybody know why the blue moon method is called the blue moon method then? Yes?
Well, stuff happens once in a blue moon.
Very good. Okay.
You know that.
Excellent. So maybe we can move back. Are there other questions? Well, then if not, maybe we can move back a little bit to the beginning of the story. And Jean-Paul, maybe you can explain us a little bit better what was the key scientific question and what else was going on around at the same time, what people were thinking that then was sort of solved via the shake idea. Sorry, shaking.
I think I will not be long because I already explained during my presentation that I was interested basically to study by computer simulation and using the multi-dynamic techniques the properties of a series of alkane in condensed phase. And so I started with butane in general coordinates, and this I did in Brussels, in my university, and then CECAM organized a workshop on long-time events, how to deal with long-time events by multidynamics. The limitation of the computing time at that time is to do a few picosecond trajectories or something like that, maybe a bit more. And then this workshop was organized by Herman Berensen, and there were people like Anis Raman, Charles Bennett, I forgot now exactly. And we were working, the 74. And there were different people working on different subtopics, how to improve MD effect. So Herman Benson was studying how to filter fast iterations to get the main trend and so on, and hoping to use larger time step. In fact, this came later with the multiple time step method, actually, which was a formal development exactly on the idea he was working on in that workshop. Anis Raman was working on water, and Fiacucci, and they
knew that by changing the moment of inertia of water, they could decrease the time scale of rotation so that they could sample the phase of water for static properties, of course, with a modified dynamics in which you slow down by changing the inertial term and getting all time scales, all characteristic time on the same level to improve your efficiency of your MD. And Charles Bennett was doing very formal things, looking at the spectrum of fluctuation in Leonard Jones' album and trying to see how to decrease the fast modes and increase by playing on the mass tensor, so on. And I was in my second or third year of PhD, and I came with an idea that we could block the fast modes with holonomic consequences. And we did that. There is a report on that in a very pragmatic way without knowing about Lagrange equation. And we just said, okay, there should be constraint forces in Cartesian coordinates. They should satisfy the third law of Newton. They should do no work. We invented a few physical intuitive arguments to find intensities of this force, and we were plugging this in the empty code, and it was working more or less correctly. And then, at the end of the workshop, actually the report compares flexible bond with a finite force constant to rigid to show that we were gaining a factor 5 in the time step. That was our big result on that day. And then I start using this method to study longer alkanes, and this gave rise to publication, but purely of the properties of decay and for longer alkanes. Then comes a different story that I stay in CECAM because Moser, he was a quantum chemist, but he liked statistical mechanics and tried to attract students and postdoc interested in statistical mechanics. So we invited Giovanni also independently and other people. And so I was working in CECAM at that time with a big computer to study decay, you see. And that's how I met Giovanni, which is another story.
So why don't you tell us the story? How did you two meet? How did you start to work together?
So you will say, I don't like mathematics, which is completely untrue. I have infinite respect for rigor and precision. I don't have done in my studies much mathematics because I did chemistry, but I like physical intuition. I like rigor of mathematics. I'm very reluctant to do mathematics for nothing, if you see what I mean. So I need an objective and intuition why we do that, and then if I have both this NV and this clear objective, I want the rigor. So I like the rigor of Giovanni because it's very good. Sometimes he brings me for hours on path that I completed down without any result. That's the point we disagree, and that's why he attacks me from time to time. Okay, that's what he was going to do when we met.
No, this is not a good reconstruction. First of all, you were parachuted in CECAM by Bellemans, your thesis director, in a miserable way, letting you fully alone. So you were there, having to solve this very difficult problem without any idea of how to solve it. And Bellemans said, dear PhD student, solve this problem and come back to Belgium. So you were there, and in Italian we say that you were crying like a cow to be killed. Okay? And you were saying, I have this problem, I don't know what to do, etc. And as you confessed today, and I liked it, once, since you were shouting in this horrible way with tears, etc., I came to you and I asked you, what the hell are you doing? Because your crying were not so detailed and analytical. And so you say, I am doing this and that. I say, okay. And then I stayed silent. Then, since I asked you what you were doing, and you were desperately looking for somebody to discharge your daily pains, you came to me and I say, I have this idea, and now I have taken these molecules, I have changed the position at time t plus h, and so that I satisfy the good. And I say, what is this cooking? I ask you. I remember perfectly. I say, what is this activity of a piggish cook? Okay?
Yeah.
You are not a chef.
I remember pig, yes.
Yeah, you are not a chef of cuisine, but you are a physicist, so you do it properly. And then you say, okay, but how we do properly? I say, no idea. And then we started discussing, and slowly it emerged that these were the Lagrangian equation of motion of first type, that the lambda was a free parameters, that the algorithm, etc. And at a certain point, Singer and Behrens gave us a suggestion that spark a star, and we found that that was reasonable. So you are cheating a bit. Okay? Fine.
So now we've established that you have rescued him. That's the.
I was
that's
the way in
official
which
version of
he
it.
stopped to be abandoned by Bellemans. And moreover, Bellemans is a very nice character, he's almost a friend, but he always considered me, I can only say in French, but perhaps Sarah can translate in English, an truand Italien, an Italian cheater, essentially, okay? Because Belgians are convinced that the Italians, in their best case, go around with a knife and at first difficulty kill the people that they are not. And so
They do good
Bellemans,
experiments also.
yeah. Yeah. Oh. And then Bellemans saw this collaboration that was even giving result, but this Italian is an Italian, so he should be a cheater, a true one. And so he was collaborating with us, but always, however, he never opposed. So he even concluded the school in '85, I remember. But it was a very strange situation. And he never admitted that I abandoned you in CECAM in a miserable way. Okay, that's the end of the story.
It's okay. Maybe you could tell us a bit more about the role of the third author on the paper. So what Berenssen's role in all this developments?
Maybe I started.
And then he can correct you.
Herman Berendsen was interested in simulating proteins from the start. So he organized this workshop precisely to see how he could improve the MD method to tackle proteins. And so he had digested, I would say, the method that we developed in some way during the workshop of '74, but he was aware, and I don't remember how, but he organized a second workshop in '76 in CECAM, at a period where both Giovanni and me, we were working there, and we participated to this workshop. I will not tell what we did, but it had nothing to do with constraints, to this second workshop, 76 on the. And at that time, in my memory, Berendsen came with his shake routine, saying, look, you are solving the equation for the alkanes in that way, Newton-Raphson matrix and so on. And I thought of another way of doing, which is much more easy to program for proteins. And this was the shake routine. Could you test whether we get the same solution? So I did the comparison for Decane, I think, between his shake routine and the matrix method for decay. And I remember I found that exactly the same. They were converging exactly to the same solution for any. And so at that time, maybe I will let Giovanni continue, but at that time we were writing the paper for 77 with two names, Giovanni and myself. And this routine of Herman came at the moment we had already completed a large part of the paper. And so finally it was added. So if you want to continue.
It's again a bit different. We were two very young people, and we had an enormous esteem for Berenson because he was a force of nature, able to program, able to create a group, etc. At the same time, we considered him a bit of a more or less non very rigorous person, and so we had a large despise for this technique to solve the equation, but we found that it was converging. So although it smelled to be a miserable trick, was fast and giving the good results. And Berenson was a very respectable scientist. So since we were very proud of our result, we wanted to be in the general move to give publicity to it. So he said to Berenson, why you don't sign with us the paper? And up to this point, Berenson had to do with our paper, and he's a very honest person. So he said, I don't like to sign a paper in which I have not contributed. However, he said, if I can add my subroutine, that created in me a reaction of almost immediate rejection in Jean-Paul that had control, that was converging a bit less of that. But he said, if I can add my subroutine to you, then I am happy to sign. Oh, and then we said, beautiful. So we had, by hindsight, this was fundamental to the success of the enterprise, because with our way to solve by matrix inversion, then iteration, the shake equation, our method would have been used much less. Instead, being the technique of Berenson very fast, he was immediately introduced in coding of protein simulation and became immediately a good achievement. So I'm sure that without shake subroutine, the story of the overall technique would have been much less good. So I think he was really instrumental for that. Although had this marginal contribution to the elaboration, but not on the algorithm. He invented a good algorithm to solve well the things. Correct?
We agree.
Very well.
Okay. So, and were you immediately aware of the impact that this method would have?
There is a nice, if I can answer, there's a nice episode on that with Bernie Holder, the great authority of the moment about simulation. Before working with Jean-Paul on constraint, I had worked with Iacucci and then McDonald on non-equilibrium, and had found this theorem that the Lewillian could be transported, etc. And this was not enough. We also found that by another trick that we call subtraction, we could measure the response of a system also to very small perturbation. So we were very proud of that, Iacucci and I. And Iacucci was an experimentalist. So if I accuse Jean-Paul not to understand very well, in fact it's false, he understands, but he does not like mathematics. In the case of Iacucci, I can say definitely that he's not reasoning mathematically. So he understood the technique in very qualitative terms. So he was much more daring character than me, so he went to the state to do propaganda for the method. And he was presenting the method empirically. Then we do this, we subtract, and then, of course, we found, etc. And this algorithm was surprising. So he met Holder and started to explain to Holder that this was a nice method. And Holder said, this is crap. Because Bernie Holder knew even less mathematics than Iacucci. So was reasoning even worse than Yaguchi. So was starting saying, you forget pathological collision and then blah, 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 blah. And in any event, treated Yaguchi in all ways. So the Yaguchi came back for Berkeley to Paris, where we were, in tears, saying, we are ruined. Older is not in agreement, etc. But I knew that this technique is behind a mathematical theorem not attackable. So we had the opportunity to go to a conference in Hungary, in which Bernie was a participant or speaking, etc. So although I, at the time, was relatively shy, I went to Bernie Older and say, strong, convinced of the beauty of my theorem. I went to Bernie Older and say, I want to speak with you, because on the subtraction you are wrong. I say, okay, let us speak. And I say, you see, you have this operator, if you transfer the operator, that's correct, and then the result is exact. So this is a theorem, so it's exact. And I remember that Older said, from this more general point of view, you could be right. Which meant I didn't understand one word of what you say, but I'm terrorized by the mathematics you have put in question. So at the moment, I have to trust you. This was the meaning of his sentence. The week after, we were still in Paris, we were back from Hungary, and he came visiting the Valley, Verlet, and CECAM. And then he went to CECAM, and we had submitted the paper, the constraint paper with them. So he came, and I still in the spirit of the tiger I was if somebody was criticizing the subtraction. I was ready to go to others say, then you admit. And he say, no, this is crap. But don't worry. You have produced a nice paper, so you can be happy. And he left. Okay.
And the nice paper was the paper.
So the paper was the paper on constraint, and so he had been impressed by this paper. While on the other, all his life, he continued to say that he's very nice, because he continued to say that I was a very good physicist, but this was crap. So he upgraded me, but people are strange. Okay, let us go.
On the same issue,
And Meretz made a lot of publicity.
I defended my thesis in '76, so 1 year before the paper was published. You ask you were asking whether we were aware of the importance of the method. I would say that I was happy with my results, but probably more with the results of butane and decane that were in my thesis than by the method that I used to develop them. Because I knew that I was the first to have simulated non-rigid molecules. I was very happy about that point of my thesis. And the method of constraint was, of course, a good method. But then a few things happened later, like I was asked by some American physicist, he wanted the right to translate my thesis in English, because I wrote in French. And then Ian MacDonald, in his book with Hansen, introduced the constraints method. So there were a lot of signs that this method was really important. And of course, and later on, of course, it came into packages and so on. But the first sign were the one I mentioned about the importance of the method. And I liked the mathematical rigor justifying the method. I was very happy about that. I didn't like so much my results, because the butane potential was symmetric, and I had a big worry that starting from initial conditions where they were all in one well, the length of the simulation was too short to really get equilibrium internally. So I was very annoyed by that. I was thinking maybe I will miss my thesis, because people will say this has no value, you have not reached equilibrium. So I was very much worried by that. Okay, stop.
Oh, thank you. So is there anything else? Yes?
How do you think the science has changed since the time when you were doing your PhD? And do you think that it has improved or it has deteriorated or other reasons?
The method is rigorous, so
No. It's a more general question. So how?
Like the way science was practiced?
I'm not sure that I understand what is the question.
Can I try to
Sure,
repeat the
sure.
question? The question is, do you think that the way in which you guys did science, in which you practice science and the people around you practice science, has changed today? And do you think that it has
For
improved
example,
or degraded?
Jean-Paul just declared that he had this problem of which was the equilibrium of the butane, because he almost reasonably, if he was in a minimum, he was not in the other. At the time, we didn't know how to treat the metastability theoretically. As you have seen by Blue Moon, now we would simply say, let us create the good family of representative, and let us compute condition average, whatever. So, of course, my personal understanding, I think Jean-Paul will say the same, of statistical mechanics has improved by a factor, I don't know, 1,000. I mean, I remember we invented the response to an equilibrium accidentally. At the beginning, we even didn't know what was a time correlation function. That's important. The sense you can do very good things also with little. You don't have to do a lot of education of yourself to be creative. You have to have some elements, and you can get a good problem and solve them. But if you are not stupid, then this is the opportunity to grow. And this comes with time. I mean, I think I was in difficulty in explaining all that I explained today. Today, to me, this seems just trivial, okay? But this is the result of reflecting on it, of coming back and discussing and seeing the implication. If this was the question, the answer is, of course, we are completely different.
Maybe I answer that. To me, the situation today is totally different from that period. That's obvious. There were much less competition. The number of researchers in the world was much tiny, and the field of computer simulation was really emerging. You could, if you had an idea, you could go for that idea for 1 or 2 years, be on in your corner and develop something. So this method was developed at a time where it was developed over many years in a totally non-competitive world. Feeling. I couldn't imagine that this would be the case today. If you have a very brilliant new idea, I think it's much more dangerous today. You should keep it for you and develop it fast with a lot of efforts quickly to publish something to settle the field. And at that time, it was not like that. I was much more relaxed. Of course, on my side, I was getting results on butane and decane that I was publishing separately. So, but
May I disagree?
Sorry?
I disagree. May I?
Yeah.
I have an example, and this is of the 80s. I think that when an idea is really good and it's difficult to find alternative to this good idea, you can have a problem in getting it known and widespread, but it will happen. I mean, Mozart died unknown, but the music of Mozart is there, okay? And for physics, as a marginal joke, I saw with my wife Amadeus, the movie on Amadeus, and there is this contrast between Salieri and Amadeus. And when I came out of the movie, I told to my wife, you think you have seen a movie about musicians. Wrong, you have seen a movie about physicists. Okay. Salieri, Amadeus, the genius and very good musician, but not a genius, etc. They are really physicists, but that's irrelevant. The good ideas are rare, very rare. The important good ideas are very rare. In the late 80s, when the simulation was already much more widespread, etc., Panagiotopoulos, a very obscure Greek PhD student, came to discuss with Gabbins and Rawlinson to great authority of the field, problem of interface, keeping the equilibrium of the chemical potential, a very difficult quantity to compute, etc. And he got this splendid idea to say, okay, instead of putting one system in which I have a gas and a liquid and the interface, let me do two simulations of a bulk gas and a bulk liquid and permit a grand canonical passing of molecules from one to the other. So I'm simulating now a grand canonical system for the gas phase and for the liquid phase. Then is me fixing the potential, and let me fix the potential at which they are in equilibrium. Okay? And I find that by simulation. And then I kill the problem of the interface. The interface energy that is killing the simulations is no more there. And I have something that is staying. I mean, the idea is splendid. It's very difficult to have an equivalent idea. Essentially got his career by this idea. He is now a professor in Princeton in chemical engineering. He has elaborated many other explanations, evolution, etc. But this remains a contribution that grew because it was a miracle. And what Jean-Paul says is perfectly good, and now the community is very large. It's full of miserable people that try to steal ideas, etc. But the good ideas are difficult to understand. So the thieves is like a very well-locked apartment, okay? The thief to enter has to work. And so they're much more difficult to steal. And I think it's not very different to the situation. Now there is a lot of rumor about nothing very often. I mean, I have discovered this and that. Things that disappear after a short while. The good ideas think something very, very good. I mean, it's difficult to have them. And when they are good, like in the case of Panagiotopolis, they essentially stay. I have another phenomenon to tell. And this, what happened with the multiple step of Tagerman and Martina, a great, great idea, by which, by playing with the Liouvillean and by separating the fast motion and the slow motion, one can not waste a lot of time when you have two time scales. The idea was splendid, and in elementary case was working very well. And when I knew of that, I said in a sportive way, I was not offended because it was a good idea. I said, let me say that in my language, I say our constraints are fucked. Okay? And then this didn't happen. The point was that the idea is splendid, but there are numerical instabilities that kill the multiple approach, the multiple time-step approach. And so this was a splendid idea, but it didn't work well. Okay? And so constraints remain. And so, I mean, we are lucky because if this idea had been good, we had seen the number of quotations go down, disappear, and the idea would be killed. Although it was good, but there was a competitor, very nice, very interesting, and same price. So why? Okay? So you are always taking this risk. There is no waste. But no, I don't think that I don't feel this. I feel that there is a lot of stupid literature. Now you publish billion papers on. Well, you were publishing 3 or 4 papers, but 3 or 4 papers were 3 were stupid and 1 was modest, etc. And then in the course of the time, one idea emerged and it was good. And now it's more or less the same. I think the good ideas are rare. They are not easy to destroy, etc. And also to get. I mean, these people that were discussing Tagerman and Martina idea of the invariant measure, they are now disappeared completely. No one is anymore discussing the possibility of what is the name of this fractal nature of the probability measure. Okay, the one is the more trained. This is crap. But this stopped Tagerman and Martina to see their idea accepted for many years, and these stupid people didn't get that they were doing something serious, so they couldn't steal. They were even despising, okay, the maximum of stupidity.
So we're essentially running towards the end of
You
the
want to
allotted
discuss CECAM?
time.
Discuss CECAM.
So I think that the role of CECAM has emerged throughout the discussion, but is there anything specific that you would like to say about it, just to conclude on a chauvinistic note for us? Like, if you say no now, it's going to be incredibly embarrassing. So please.
No, it's, I think it's very important. The university are an isolating place. In university, it's very good if there is one professor specifically minded of something, and this group. And this group, of course, depends on the quality of the professor. CECAM offered to a professor without at the time anymore any idea, Bellemans, to send the student there to solve a problem. And then this person found Berensen maniacal about the same family of problem and much more innocent. And he was very much affectionate to the possibility of CECAM discussion. He was discussing the question with the most spectacularly qualified people of the field. And then Jean-Paul was there and found A, the discussion with Raman, the discussion with Berensen, etc., and B, me being there, available to discuss. Why not a new idea and a new pig? Okay, so it was good. And then we could advance, but we were continuously in contact with people giving us good suggestions, Singer in lab, etc. So CECAM was not simply accidentally, was structurally an instrument to accelerate enormously the possibility to produce good ideas. And this was because it was joining the mobility of the ideas, the put together, etc., the seriousness of the discussions, and the presence of younger people looking for something good to realize. And this was, in a sense, was an explosive mixture because Americans invented simulation, but simulation got in those years much more development and success in Europe than in America. That's spectacular. And if you look at the centrality of CECAM for that, is enormous. Binder, Verlet, etc., have not been able to create the same resonance. And this formula, I think, has to be, is not necessary that be in CECAM, but has to be kept as a good model for fast development of a new discipline.
Jean-Paul, would you like to conclude?
Just the issue of this workshop, which were successful in the in the 70s and in the 80s, it is discussed every CECAM meeting by the organization because this costs some money and people would like to know whether it is useful to invest the money in long workshops or in short workshops. This debate is going on. And, we took profit of this long workshop for sure because the contact with the other people was not punctual, it was for a long period. So you had a discussion, it was generating some ideas, you were trying things, and 2 weeks later you were going back to the same person and discussing.
But we discussed together the case of the Blue Moon, that instead was produced exactly when the long workshop were out. Still, the idea of the workshop to bring together the specialists of a problem to discuss in a very informal atmosphere for 1 week, not much, created the seeds to some developments.
Okay. But then there was a series of workshops. Huh? So this is another sustaining.
That's the way. I mean, it took 3 workshops to get the collaboration, focused collaboration starting. But again, these 3 workshops were in CECAM. The human reason we discussed are sometimes ridiculous even, but still it's important to understand that if you realize this also for a short time, then the circulation of idea is much higher. And if you have the good will, younger people wanted to invest on something, they profit enormously of this kind of exchange, and things go fast. So the computer was the first opportunity, no? You had to meet there, etc. But then the formula remained because it's still creative, although if the computer is no more the center of the issue, although it's still an important issue.
Okay, so I think I speak for the director when I say that we try to keep up that spirit here, no? So the fact that, so thank you very much, Giovanni. Thank you very much, Jean-Paul. Thank you to all of you for staying with us this afternoon. I hope it was interesting. And I just wanted to mention that we have already planned another one of those, should you assess. And that's going to happen, oops. Yes, okay. On the 25th of July, just after the CPMD meeting here, and it's going to be Carparinello Molecular Dynamics, explained to us by Ryckaert and Michele Marinelli. Thank you again. Have a nice day.